So this is the lecture 7.2 that we have on microscopic polarization. So mainly we will be discussing the Clausius-Mosotty relation. So I will try my best to explain to you what is the difference between a local electric field, and this is then the field that is being felt by nanoscopic building blocks that we have in our solid. So that then they could be, for example, the molecules or atoms or whatnot that form our crystalline piece of a material. And then what is the difference between this local field and the incident field that is actually being applied on this macroscopic piece of our solid. And this concept of local electric field, it also results in conditions that are known with the names of Clausius-Mosotty relation and also the Lorentz equation. So I will very quickly derive these equations and try my best to explain to you the meaning and their relevance in terms of light matter interaction in a piece of a solid. And before I get started, I would like to point out that yes, of course, when we are thinking of dielectrics, like the optical responses are often quite many times of interest in terms of applications, because in dielectric materials, due to the fact of band gap, these materials are really mostly transparent due to propagation of electromagnetic radiation. And then subsequently, we may use them in many different kinds of applications. So let's go through our quick derivation of the Clausius-Mosotty relation, and I will start this by essentially linking the macroscopic polarization density, so the P field that we defined in the earlier lecture when we were discussing Maxwell's equations, the macroscopic formulation of macroscopic equations, and I will try to link this macroscopic quantity into the microscopic quantity, and this microscopic quantity of interest that is describing to us what is the response of a kind of like nanoscale building block of our piece of a solid. So this material or this response will essentially be known as a microscopic dipole moment P. And simply the macroscopic polarization field, capital P, is being defined, and it's in essence the microscopic dipole moment P divided with the unit volume of our solid. Another way of writing this is that we have the N, the number density of our piece of a solid, times the microscopic dipole moment P, and this gives us our macroscopic polarization field, P capital. So V is the unit volume, and another way of writing this equation is N with N, so N is the number density. And this dipole moment P, we can link this to the electric field, and this electric field would be our incident field. It could be, for example, optical field or static field, depending on what will be our problem we want to solve. And these two quantities, the incident field and the created dipole moment or induced dipole moment, we can write their relation using a polarizability alpha as a material parameter. And essentially, like this polarizability alpha that gives us the kind of response on the microscopic scale from the matter is being defined with an equation, so that we have the dipole moment, and that will be equal to the polarizability alpha times the epsilon naught, so the vacuum permittivity, times the local field. And please note here we have the local field and not just whatever incident field, but rather the field that actually is being felt by this nanoscale object. So E log is the local electric field, and that may, in fact, depending on the piece of a material, actually be quite different from the incident or applied field. So mathematically put, like the local field may be different than the incident field. And this is like our main point that we want to make in this lecture, that due to the fact that we have a periodic crystal, the periodic arrangement may also change the way the local field is. So it may not be equal to the incident field. And incidentally, the same physics happens also in terms of nanoparticles and metamaterials and or nanoscale optics. So in many times in research and in applications, we are in a conscious way, we want to modify this local field. So we may, for example, want to increase the local field so that we can kind of enhance the incident field. And when the light matter interactions of question will be of our main interest, then we will be interested in kind of changing, modifying this, increasing that, so that the subsequent light matter interaction would be stronger, for example. So in a way, this is not just related to a solid state physics that we are discussing here. But the same math, of course, happens in many different problems and many different topics. So I just wanted to point to you that these things actually are of relevance also, not on just solid state physics. So, as I promised in the previous lecture, our problem or our interest that we want to find out how things work out is that we want to find a relation between the macroscopic field E. So this is our incident field and how that gives rise to a macroscopic polarization. Because if we know what is the macroscopic polarization, and we certainly do know the Maxwell's equations, then we could calculate and understand how matter interacts with incident light or incident electric field. So this is our motivation. So if we have P, the material polarization, then we may describe the macroscopic response with some kind of material parameter, and that will be a chi, known as a material susceptibility. So the created macroscopic polarization field, that is the response of our material to an incident field, that's equal to the epsilon naught vacuum permittivity times chi, the material susceptibility, times the incident field. And here, this field is actually the incident field. So we are speaking of the macroscopic fields and not the fields that are actually being felt by these kind of nanoscale objects, for example, the molecules or atoms that make out the macroscopic solid. So please note the difference between the fields, the macroscopic field and the microscopic field, and the macroscopic material polarization and the microscopic dipole moment P. So chi is the material susceptibility, and this is often what we would want to be able to calculate, because if we would be able to calculate that, then we would know how the system would respond to incident radiation. And the microscopic local field, now this is the kind of quantity that is more associated with the microscopic dipole moment. So please compare these two equations. We have the equation for the material polarization above, and then we have a equation for the microscopic dipole moment P, small p, and that is equal to the molecular polarizability alpha times epsilon naught times the incident local field. Sorry, I shouldn't say incident local field, but the local field felt by this molecular sized object that is being described by this molecular polarizability. So these equations look quite similar, and please, I recommend you to even memorizing these, because if you can remember them, probably you can avoid confusing these two different fields from each other. So this is the local field actually felt by a kind of microscopic object that is being described by polarizability, and that gives rise to a microscopic dipole moment, small p, and here we have the incident field, a macroscopic field, and then we have the material polarizability, the kind of like a big chunk of a material and its response, material response susceptibility, vacuum permittivity, and that gives rise to a macroscopic source polarization or material polarization. So these equations are important to remember. And here I'm trying to elucidate what happens when we actually are having a periodic substance at our disposal. So in the A figure, we have the incident field, and if you only have let's say a single molecule that is being interacting with incident light, incident electric field, then the local field will also be exactly equal to the incident field. And this is the scenario that we are highlighting here. So then this molecular, for example, molecule may start oscillating at the same frequency as our incident field, and then it may scatter light, and part of the light may also be absorbed into the molecule. And in the case when we actually have a macroscopic solid and not just a single molecule or atomic emitter anymore or scatterer, but rather we have a periodic substance, then we have an incident field, and the incident field is hitting many atoms, many molecules inside our solid. They are even periodically arranged, and this then affects how these different atoms are being scattering light. And because of this process, that there are many scatterers now instead of just a single scatterer, in total, this field that is being felt by each of these different atom-sized emitters or scatterers, the local field, E log, is not anymore the incident field. So this is the main difference. Please have a look on this figure and try to understand what happens. If you have a just single scatterer or emitter absorber, then the local field is exactly the incident field. But when in fact we actually have a piece of a material, then we have many scatterers and they scatter light, electromagnetic radiation, and subsequently the local field will be modified. So here, that small emitter is essentially like our microscopic dipole moment P, and that scatters light, the incident light, and it also can absorb and re-emit the incident light. And what we want to do here next is that we want to somehow link the microscopic and the macroscopic quantities together, so that then if we would, for example, be able to calculate the microscopic response of our substance, so we would do like a material science related solid state physics, then we would tell to a more optics related person that how now you can actually calculate this macroscopic quantity, and now you can actually understand your experiments. And then how do we do this? Well, I will first of all note that how we would actually calculate the local field. The derivation is beyond our scope. You can read it from existing textbooks. We just are happy in outlining the main equations and the main principles in this approach. And we assume that we have an isotropic dielectric medium. So basically isotropic means that it looks exactly the same in each different directions. That helps us out so that we don't need to consider anisotropic responses. And we have a dielectric medium so that we know that light actually is being propagating inside. It's not a metallic piece, and we don't need to worry about free currents being formed much. And if you're interested, please have a look on Jackson's book. So John David Jackson's book, Classical Electrodynamics. There's actually a lot of very useful and interesting things there, but the derivation of the local field is also being given by John D. Jackson. Very math-heavy textbook, but very good also from the point of view of description and completeness. So the local field, without like any derivation, now please drums. Somebody has done the derivation already beforehand, and we can just use the result. So the local field is the incident field plus some kind of contribution from the source polarization in itself. So the local field is then of this form. So we have the E plus 1/3 times epsilon naught, the vacuum permittivity, times the material polarization P. And this allows us to write an equation in terms of the polarization. So we can solve the above equation with respect to P. And this gives us the relation that P, first of all, remember the defining equation. So P is equal to the particle number density N times the dipole moment. And then we can place in that the dipole moment is of a form epsilon naught times alpha times local field. And now we equate this with the equation we can solve for from the above equation. And now we have a relation that we have P equals N times epsilon naught times alpha times E, the incident field, plus 1/3 times epsilon naught times P. So this is like how we can easily use this. We insert local field into here, and this is basically the defining equation for the source polarization. And this is also giving us the defining equation for the dipole moment. And now we end up with this. And now the trouble is that we have P on both sides. So we must solve this with respect to the source polarization only. So we just do a little bit of mathematics here, and then we end up with the correct solution. So P, that's equal to the term we had previously. So this is what we had earlier. We can multiply the n epsilon naught alpha into both of the terms inside the parentheses. So we are left with this term plus a term n epsilon naught times alpha divided by 3 times epsilon naught times P. Of course, the epsilons now vanish from the latter term, so that on the left-hand side, we can have a term where we have the source polarization, 1 minus n times alpha divided by 3. So please note the vacuum permittivities have disappeared from here. And then on the right-hand side, we have the second term, or the first term. So we have the n times epsilon naught times alpha times E. So essentially this term now on this side. And now we can divide the term inside the parentheses to the right hand side. So we are left then with the P being equal to vacuum permittivity times something inside the parameter. And this is actually being defined or gives us the material susceptibility chi. So please note, remember the equation for capital P, the material polarization as a function of chi. And then this is, we multiply with the incident field. So in other words of writing things like we are essentially taking use of this equation here. So P equals epsilon naught times material susceptibility chi times incident field. So this term now is our material susceptibility. For most materials, and especially when we are at long enough wavelengths, these polarizabilities alphas, they are positive valued quantities, so alpha is larger than 0. And what this implies, we can look into the equation. If you would like calculate or estimate what is this local field corrected susceptibility, we would note if you put a positive alpha into our terms inside the parentheses, so we put a positive valued number here, we see that this kind of local field corrected material response, the susceptibility term here, is actually larger than the simplistic chi equals n times alpha prediction. And please note, like this would be the case that we would have the relation when there would not be this kind of like a notion of local field. So if the local field that is giving rise to the microscopic dipole moment, if that would be the incident field, so then we would really have this simple prediction. But that is not the case, as we can see here. So this is the kind of contribution that we have due to the fact that these particles or substance that forms our piece of a solid, it scatters light, and then we should really correct the material response due to the fact that we actually have a local field that is different from the incident field. And in fact, most of the time, this is larger than the material susceptibility. This local field correction increases in a way the light-matter interaction, makes it stronger. And sometimes if you do things right, or you are fooling around with kind of artificial engineered materials such as metamaterials, you can actually make this difference quite dramatically large. And then this is also what we are doing here on our optics department, optics laboratory. And finally, we connect chi with the relative permittivity, epsilon r. And if we have the relative permittivity, then we can certainly also estimate the refractive index of our dielectric medium. So please recall that the relative permittivity epsilon r is equal to 1 plus chi. So then that's the relation. And then we can plug this to the earlier relation we found for the material susceptibility chi. So chi is equal to epsilon r minus 1. And then we know that the chi is also equal, as we previously discovered, to n times alpha divided by 1 minus n times alpha per tree. And we can shuffle things around. We can write the latter term on the left-hand side. So this 1 over n alpha per tree on the denominator, we can multiply that to the left-hand side. So we are left with epsilon r, the relative permittivity of our substance, minus 1 times the term inside the denominator. So 1 minus n alpha per 3. And this is equal to n alpha. And now we can multiply these terms inside the parentheses together. So we are left with epsilon r. And then we have epsilon r minus n alpha per 3 minus 1 plus n alpha per 3, if I did the math right, and that equals to n alpha. So we just basically multiply those terms inside the parentheses. And then with this at hand, we can simplify things further. So we can write that on the left-hand side, we have epsilon minus 1. So essentially, like we have this term and here this term, and we put these other terms to the right-hand side. So then on the right-hand side of the equality, we have n per alpha per 3, and then inside the parentheses 2 plus epsilon r. So this should be what we have here in case we did things right. And now we can have the terms that have the relative permittivity on both sides. We can make a fraction out of them, so we have related. We end up with epsilon r minus 1 divided by epsilon r plus 2. So we basically just multiply this term from the right hand side into the left hand side, and then we are left with this term on the right hand side of the equation. So this is what we have. Depending, I did not have use this epsilon naught in the derivation, but this equation that we have here is known as the Clausius-Mossop relation. Depending on which kind of unit system you're working with, we may either have this epsilon naught here or we don't have. Depends really on the kind of like a unit system that people are being used. And this is one of those rare occasions that we are still having in certain communities Gaussian units and not the SI units. So please be very careful if you ever end up using these kind of equations, or if you're working with dipole moments and material polarizabilities, so molecular polarizabilities. So be very, very careful of using the right systems of units. So there is this Gaussian system of units, CGS, and there are the more often used SI units. And there really is a lot of confusion and hassle in terms of the units and way the polarizability alpha is being defined for a substance. So if we are dealing with the Gaussian units, so in CGS, the unit of alpha is 1 over m squared, and then the permittivity epsilon naught is many times actually hidden inside the polarizability, so that we would not really have this epsilon naught here in the equation. And please note that this is actually like one of those cases that you might really end up, lots of hassle and confusion of not knowing when to have this or when not. And this is also many times that when you write the dipole moment equation, please be very conscious about this. Do you have the vacuum permittivity there or not? So that then you should be asking yourself that is this an equation in the Gaussian system or in SI units, and what is this confusion? I've spent a lot of time in my life in trying to kind of find out mistakes in equations and math because of this hassle that different sources and different people use different units, and there really is a kind of like a confusion many times in the papers. I myself always try to use the SI units. I've been schooled to use them and like forced to use them, but it's not always the case. And now that we have the Clausius-Mossop relation, that essentially tells us that depending on what is the molecular polarizability, the relative permittivity may actually change slightly, and depending on the kind of particle density, how dense of a substance we have, the local field corrected values for the material relative permittivity. And now we can also describe this in terms of the refractive indices. So please recall from classical electrodynamics and optics that the refractive index of a substance, it's been defined, then it's actually it should be the other way around, so that it's the it's the right way. So that the refractive index is being defined that it's the speed of light in vacuum divided with the speed of light inside the material, and then plugging things here. what we have is that we have epsilon, the permittivity of the material times the permeability of the material, mu divided by epsilon naught per permeability naught, so the vacuum permittivity and vacuum permeability, and these inside the square root. And in the case of optical materials, so when we are not having a magnetic material and magnetic response, then the magnetic permeability mu is essentially close to the vacuum permeability mu naught, and then this relation turns into the square root of relative permittivity. So this is the usual relation that we use to describe refractive index. And now that we have the Clausius-Mosotty relation that tells us what is the relative permittivity, we can pretty simply calculate or describe the Clausius-Mosotty relation with respect to the refractive indices. So what we are left with is we can do the replacement, and then we can write an equation where we have the Clausius-Mosotty relation, the first left-hand side term for the CM relation, epsilon r minus 1 divided by epsilon r plus 2. So we can now replace this with the square of the refractive index. So then we end up with a relation where we have Clausius-Mosotty relation described using refractive indices. And this equation, this latter equation or equality, is known as the Lorentz equation. And this is also many times used so that we can then, if you would know what is the kind of microscopic response of our piece of a solid, what is the molecular polarizability, and if you know the density of these polarizabilities, we can estimate what will be the macroscopic refractive index of our substance. And with these at hand, we have now essentially found the basic relations that we can use to connect what are the microscopic quantities and then what are the subsequent macroscopic quantities. So in a way, connecting this solid state physics, the branch of physics where we are very much interested in being able to calculate the microscopic quantities, in this case, the capital N and alpha, and then we are able to relate them with the microscopic quantities. So a refractive index or relative permittivity, which is a quantities, or which are quantities that are very much of interest for people who are dealing with optics or electrodynamics. So that's the kind of main thing that I wanted to teach you during this lecture. So I thank you for your time and patience, and please join me on my next monologue when we are starting to look into the frequency dependence of this relative permittivity. So that depending on the frequency of incident electrodynamic radiation, electromagnetic radiation, then the response, the alpha may actually be different. But more on that on the upcoming lecture. So thank you for your time and patience, and enjoy the evening, the night, and the morning. Thanks. Bye-bye.